Good morning, students. Is voice clear? Everything reaching clearly to you? Yes, students? Yes, sir. Okay. So, day 7. And day 7, we are starting gravitation. Important chapter. You can expect at least 2 questions from this chapter. Okay. So, gravitation is important. And gravitation, what we are starting with? We are starting with Kepler's law. Okay, from the back side. We are starting with Kepler's law. Okay, 3 laws are there. What are the conclusions? We'll see them. So, first law of Kepler says that the planets which are orbiting around the sun, that orbit is not circular. It is actually elliptical. Okay, the orbit in which planets are revolving around the sun is elliptical orbit and not the circular orbit. Okay, fine. It's elliptical orbit. Fine, something like this. In this one, if you are talking about ellipse, then there is something called major axis and there is something called minor axis. Okay, so major axis and minor axis. Okay, this is major and this is minor axis. Right. So what he says is, Kepler said that the planets orbiting around the sun, planets are orbiting around the sun in elliptical orbit. Okay, then what is the other point? Other point is the sun is at its one of its foci. Foci means focus. So there are 2 focuses are here. One is here and one is here. There are 2 foci, say F1 and F2. And you can place sun at any of the focus. Okay, so we are placing it here. Okay, so what is the second point? Planets are orbiting around the sun in an elliptical orbit and the sun is at one of the foci of the ellipse. Okay, here is the sun. So now what you can see is, suppose there is an orbit over here. Not orbit, this planet. Okay, planet orbit we have already made. So this is a planet. Okay. So if this planet is orbiting around the sun, you can see here it is farthest and here it is closest. Okay. Here it is closest, here it is farthest. And if suppose we say our major axis is of length 2a. Okay, and minor axis. This is minor. Minor axis length is 2b. Okay, then this distance here is called AE. A is what? Semi-major axis. This is called semi-major axis. So this is AE. Right. Then what is the farthest distance? This is farthest we are saying. RF. So RF becomes A plus AE and this is the closest. RC. RC becomes A minus AE. Now what is E? E is eccentricity. Okay, and its value is constant. Okay, like for Earth, its value is constant. For any other planet, its value will be constant. Okay, that is eccentricity. So this eccentricity will be constantly given to us and major axis value will be given to us. So we can easily find out what is the closest radius and what is the farthest radius. Okay, so that's important for us, just remember. Okay. This is the conclusion of the first law. So we got that what is the closest distance of the planet from the sun and what is the farthest distance of the planet from the sun. Okay. Then what is the second law? Second law says that aerial velocity of the planet. Aerial velocity. Aerial velocity means area swept by the planet per unit time. That's called aerial velocity. So aerial velocity of the planet is constant. Aerial velocity of the planet moving around the sun, moving around the sun is constant. Okay, now we know that the planet is moving around the sun in an elliptical orbit. So this is elliptical orbit here. Okay, and the sun is where? One of the focus. So sun is somewhere here, let's say. Okay, and planet, let's assume, is once here. So what will happen is, planet is going to move. Suppose it reach here. Okay, it reach here in time t1. So what is the area swept? Area swept is this. Okay. Okay, this and this, because initial and final positions are these. Okay, so see now, this is the area. This area. This is swept by the planet in time t1. And suppose next instant, the same planet is somewhere here. Same planet is here, and then it is here in time t2. Okay, so again, join this. Okay, then again, join the other one also. Right, so this, if I say this area here is A1, okay, if this area is A1 and this area is A2, then aerial velocity means A1 by T1 equal to A2 by T2 is constant. Instantaneously, if you want, dA1 by dt is equal to dA2 by dt. Okay, dA1 by dt equal to dA2 by dt. Area swept by the planet per unit time is constant. This is the law. But what it gives us, what it is going to give us, when we solve this one, area means what? This area. Okay, so when you are going to solve this one, you get is, this is what triangle we can do, make it or not. We can make it as a triangle. When, if I am going to make it very small, time I am going to make very, very small time, then what will happen? You just see. If I take time very, very small, then I can make this triangle like this. Okay, I hope it's visible to you. Let me make the frame of that. Okay, see now, this is the triangle. If I make time very small, now it looks like a triangle only. See. So this I would say is radius, and in this direction, let's its velocity is v1. Okay, so what is this height? If suppose time I am going to take as dt, then I can say that this area, the small area that is there, this one, I can say that is half r1 v1 dt. This will become the area. Okay, then I can say half r1 v1 equal to, let's write this is dA, okay, dA1 by dt. That means that is only the area swept per unit time. So area will come out to be half r1 v1. So if dA1 by dt is like this, so here also dA2 by dt also will be like that only. So dA2 by dt will be writing as half r2 v2. And since Kepler says that both are constant, both are equal, so conclusion is R1 V1 will be equal to R2 V2. What is R1? R1 is the distance of the planet from the sun. R2 is also distance of the planet from the sun. And V1 is velocity of the planet at that moment. V2 is velocity of the planet at other moment. So R1 V1 equal to R2 V2. Conclusion of Kepler's second law. Now, if the same planet is moving here, so I can write like this also. No? M R1 V1 equal to M R2 V2. Obviously, we multiplied them both sides. So this becomes conservation of angular momentum. Angular momentum of planet around the sun. Planet around the sun is constant. Around the sun is constant. Okay, so these many things are there from the second law. First, aerial velocity constant. This aerial velocity gives what? R1 V1 equal to R2. And this R1 V1 equal to R2 V2 give us what? Finally, conservation of angular momentum. Right, so this is second law. Let's see third law also. Then we'll solve few questions on this. Third law is also very important. Many questions are asked on this. And what is third law? Third law says that square of time period of the planet around the sun is directly proportional to cube of its effective radius. T square is proportional to R cube. Very, very important. Okay, so these are the three laws of Kepler. Now, let's see what type of questions can be asked from us. Okay, so question is asked from us is, if I am going to take elliptical orbit based on second law, okay, sun is here, right, any radius is given, the distance is given here, suppose this is r, okay, and here velocity is v. Here velocity of the planet is v. Then what is the velocity when this distance becomes r by 4 or radius becomes r by 4? Here velocity of the planet is v. What is the velocity here? That's the relation. What is v1? Very easy for us. What you can do? We know that r1 v1 equal to r2 v. Right, this is r, this is v. This is r by 4 into v1. R and r gets cancelled. v1 equal to 4v. Very simple. Okay, one more thing is there. Apart from Kepler's laws, whatever the Kepler's laws has given the conclusion. Because gravitation force being a conservative force. Right? Gravitation force is conservative force. So, energy also remains constant. Which energy? Mechanical energy. Remember that. System's total energy always is constant. Going back and writing, okay? Here I am writing it. Mechanical energy of planet and the sun is constant. That means mechanical energy at one position must be equal to mechanical energy at other position. That is potential energy at position 1 plus kinetic energy at position 1 equal to potential energy at position 2 plus kinetic energy at position 2. So yes, angular momentum is conserved, but other than that, energy is also, mechanical energy is also conserved in sun and the planet system, or later on maybe earth and the satellite system. Okay. Alright. So see now, this question we have solved. Correct? No problem in that. Okay. Then what are the other questions? Other questions can be a planet is orbiting around the sun in nearly circular orbit of radius r with time period t. Okay, find time period of planet if effective radius is 2r. What to do? Simple. We know that we have a relation called t square is proportional to r cube. Okay, so he has given t1 square. What will do? Take ratio will take t1 square by t2 square equal to r1 cube by r2 cube. Okay, so t1 is given t, t2 we are finding, r is given as r only, and this one is given 2r. Okay, so you can see that r cube I can cancel. So what we have? T square, and this is 8. So 8t square equal to t2 square. So what we have got? t2 is equal to 2 root 2 t. This is the time period of new planet whose radius is 2r. Okay. Then what more questions we can do on Kepler's laws? Awkward questions, awkward values also is given to us, in which we can solve this one. What awkward? Radius will be 3 by 2r or maybe 3r by 4 or something like that. Also questions can be asked from us. Okay. Alright. So now let me ask you one question. Okay. It says find time period of planet if effective radius is 27r. Okay. When time period of planet with radius r is 2 hours. Okay, so this is question given. Simple question again based on that third law. T square is proportional to r cube. Correct. So what is given? Again, same thing. T1 square by T2 square equal to r cube, r1 cube by r2 cube. What is there? We are finding first one. So T. Second one is 2 square equal to 27r. And this one r cube. So r cube and r cube is cancelled first. Then t square equal to 4 into 27 cube. Right. Then what will happen? T equal to square root of this 2. Square root of this is what? 27 root 27. Okay. So 54 into root 27. Root 27 we can write as 3 root 3. So 3 root 3 hours. Okay, so like this questions will be coming to you in the form of Kepler's law, right? Already conclusion I told you. Second law's conclusion, V1 R1 equal to V2 R2. That also you can solve a question on that. We have done, I think. V1 R1 equal to V2 R2 in equation we have done, right? Yes, we have done it already. Okay, so either it will be on V1 R1 equal to V2 R2 or it will be on T square is proportional to R2. Okay, let's move ahead then. Now, gravitation force. So, gravitation force between two masses, M1 and M2. Separation is R. Okay, so both the masses are applying gravitation force on each other. Force applied on M1. Okay, force applied on M1 by M2. So, force on 1 because of 2. Attraction like this. Same way, force on 2 because of 1. It's like this. Equal and opposite. So, if they are equal and opposite, I can say that this is action reaction force. And as we discussed before, action and reaction both happens to be on different bodies. You can see that. Okay, action is on M1, reaction is on M2. So, it's action reaction force, right? So, this F1 and F21, their value is same or different? Same. Magnitude is same. You talk about F12 or you talk about F21. Okay, vectorially if we write, their magnitude is equal to what? G M1 M2 by R square. Right. Vectorially if you want to write, F12 is equal to negative of F21 because their direction is opposite. Okay. Now in this relation we all know G is gravitation constant, M1 M2 masses, R is distance between the two. So G is gravitation constant and its value, this is gravitation constant. Its value 6.67 into 10 to the power minus 11 and its unit Newton meter square per kg square. Okay, dimensions are what? Newton's dimension we know this MLT minus 2. Meter square means L square. Kg square means M square. So dimensions are M to the power minus 1, L to the power 3, T to the power minus 2. Okay, M to the power minus 1, L to the power 3, T to the power minus 2 is dimension of gravitation constant. Okay, now we are writing properties of this force also here. So it's action reaction force. Okay, then it's conservative force. Conservative force means what? Work done by them depends only on initial and final positions. Okay, and work done by them is equal to negative of change in potential energy because it's conservative force, right? Third point, it's central force. That means the direction of this force is always along the line joining those two masses. Suppose it's a bigger mass, spherical thing is there, then where is the mass of spherical object? At its center. So from center to center it acts. That's why it's called central force. See, this is from this mass to this mass, along the line joining the two masses. That's why it's called central force. Okay, so action reaction force is there, conservative force is there, central force is there. Then this force does not depend on medium between them. Does not depend on medium between two masses. This force does not depend on medium between two masses. Okay. So whether you keep in water, whether you keep in glass, whether you keep it in vacuum, force between two masses will be same on. Right. What more? It's a weak force. It's a weak force. When it will be significant? When one is heavenly object, like Earth is applying on us, then it's huge. it has got value. But if we say that one object of 1 kg and another object of 5 kg, how much is force between them? It's negligible. Okay, so it's a weak force. Next point, fifth point here I am writing. It's weak force. Okay, so these are basic things, and then again it's a vector quantity. So if there are more than one masses are there and they are applying the force on each other, then force on any particular mass due to all will be found by vector laws of addition, parallelogram law. Okay, so we say that it follows superposition principle. Okay, so gravitation force follow superposition principle. Superposition principle means vector addition. Superposition principle. Okay. Now on gravitation force also many questions are asked. What questions are asked? If you see any book, then you'll find many questions like this. What they will do is, they will say that, okay, I'm just making a question like this, okay. M1, M2 is here. Separation between them is R. Okay, so they say that find the force between two masses, these masses make equal, okay, make them equal, M and M. Okay, find the force between two masses if their masses are doubled and separation is halved. Something they can give you, okay, masses are double or masses become half and separation become 3 times. Many times you'll find this question. Very easy, no problem in that. Initially, okay, we know that the force actually is Gm square by R square. Gm1 M2 by R square. So this is the initial force. Now they are asking, when masses are doubled and separation is half, then what is the force? So okay, F1 G into 2m whole square by R by 2 whole square. Right, so what this has become? G is 4G m square by R square by 4. This is 16 Gm square by R square. The force has become 16F. This is F, this is 16F. So many questions will be like this. Alright, let's see further. What more? Basic questions are this way also. If they say that there is a combination of particles which are kept at the vertex of the triangle. Here is M, here is M, here is M. Then a particle is placed at the centroid. Okay, this is centroid. Then what is the net force on this? So what is happening? This force, this M is applying the force on this like this. This M is applying the force like this. This M is applying the force like this. What will be the net force? Net force will be 0. Okay, net force is 0. Okay, because this angle is 120, 120, 120. Okay, so it's an equilibrium basically. This particle is in equilibrium. The net force is 0. So when this force is 0, whenever we have a regular shape, okay, and the particle is kept at the center, and all the vertices are having same mass, then here force will be 0. In fact, gravitation field is 0. That's why force also will be 0. Okay, what is 0 here? Gravitation field. That's why I am calling this as an equilibrium. Okay, this is equilibrium. Not only here, if you have hexagon also, a shape of hexagon or pentagon in this one. Yeah. Okay. So this is pentagon. Now suppose that all the vertex I have M, M, M and M. And here this is the center point. And here also M. So if I ask you what is the net force on this, it says 0. Okay. Net force and the particle kept at point P is 0. So remember, the regular shape, all the masses are same, and we are keeping another mass at the center. The net force on this is 0. Same in electrostatics also we are going to see. Okay. But now, if we twist this question, how we are going to twist it? See. In the same triangle. Okay. And we say that here is M, here is M, and now find force in the particle, on the particle at the center. The twist is like, now what we'll do? We'll first find the force because of this, then find the force because of this, then add them, and then we'll be getting the answer. Okay, normal. But smart method is, we'll assume that there is force here, there is mass here. This we assume. So when this is also there, then the net force is 0 on this particular mass, right? So it means the force applied by this upper one is equal to the force applied by these two. Yes or no? Correct. Then only it is 0, no? See, F1 plus F2 plus F3 equal to 0. That's what we are saying. So that means if I say F1 is equal to what? Minus of F2 plus F3, no? So magnitude is equal to this. Right? So that means force applied by this is equal to the force applied by these two. So why shall I calculate these two? I will calculate this force only. Only F1 I will calculate. So what will be F1? F1 will be G M into M. Now what is this? Now I have to give you the side. Okay. So if suppose that this is equilateral triangle, this side is L, this side is L, this side is L. Then how much will be this? This will be L by root 3. Okay. Distance of centroid from the vertex, L by root 3. So L by root 3 whole square. Finished. I am not calculating anything else. C Gm square by L square is my answer. Instead of calculating the force because of these two, I calculated force because of this alone. Can we apply this in all regular symmetrical bodies? Heptagon, hexagon, pentagon? Yes. Fine because of one. If suppose that one mass is missing and they are asking you what is the total force, put the mass at that missing position and find the force because of that itself. That is our answer. You don't have to calculate because of others. Okay. Then what more we can do? We can find the force because of uniform bodies. Uniform means is suppose that we take one small rod and its length is L and mass is M. Right? And we want to find its force on another particle. This I'll make it as M1 and this is M2. Okay, and this distance is given as B. So force between a rod of mass M1 and particle of mass M2. Particle of mass M2. Right? Okay. So now what we'll do? Now gravitation force, the law which defines that is Newton's law. And Newton's law is defined for particle system. That means two particles. Okay, but this is not a particle, this is a rod. And mass is throughout distributed. So what to do in this case? Take particle, small particle which we can say is a particle. Okay, so this is dm. It's very small. Okay, but since it's a part of rod, so it must have a length also. This length will say dx. Mass is dm, length is dx, and the separation from here to this one is x. So what is the force? Say df is equal to g dm is dm into m2 by x square. Now what is dm? Now whenever we say uniform, uniform means is mass per unit length is constant. Mass by length is constant. That means m2 or m1 is what? Mass of the rod. And what is its length? L. So m1 by L must be equal to dm by dx. Why? Mass by length is constant. It's uniform. m1 by L equal to dm by dx. Or sometimes this m1 by L is called as lambda, linear mass density. So in that case, we will be writing dm equal to lambda dx. But here what is it? Dm equal to m1 by L into dx. Okay, so put it here. G m1 by L into dx. Okay, multiplied here m2 dx by x square. Now what we'll do? We'll integrate because we know that similar particles are there throughout the length, and integration will solve it and give our answer. So from where to where now? This x value is changing from where to where? This dm could have been at this point. So your x value could have been d. Same way dm could have been here also. Then the distance would have been d plus L. Okay, so minimum distance is d when your dm is at this point, and maximum is when dm is this point. That means d plus L. Integration dx by x square is minus 1 by x. So minus g m1 m2 by L 1 by x. Here is d, here is d plus L. So what we are getting? Minus g m1 m2 by L 1 by d plus L minus 1 by d. Now multiply this negative inside. So this changes into g m1 m2 by L 1 by d minus 1 by d plus L. That is it. Okay. So this way we can find the force due to uniform objects also. Correct? Right? Okay. Then what more? What more we can do? Or in place of question, let's go on to the next topic. The next topic is gravitation field. Gravitation field. Gravitation. Now what gravitation field is? The region around any mass in which if you are bringing any mass, that mass will experience gravitation force because of the other mass. Means, if suppose I am talking about this M, so region around this, suppose this is the region. In this region, if I am going to bring any mass, that mass will be experiencing gravitation force because of M. Okay, the region around M in which any mass experience force due to mass M. Now suppose its region is this only and you brought one mass over here. This is not going to experience any force because of this. So that means you are out of gravitation field of this. But as you brought in, there will be force. Okay. So this gravitation field we experience, or rather write with E. What is its value? We say that E is actually equal to gravitation force per unit mass. Which mass? Which you are bringing? This mass. Normally we say unit mass we are bringing. Okay. Or unit mass means is which is not going to have any effect on the gravitation field over here. Okay. So E is equal to F by M. If suppose we are bringing it over here and this is X, so then what will be its value? Say G m m by x square, and then this mass gets cancelled. So E value is gm by x square. And what is its direction? Direction is same as gravitation force. So on this mass, how is gravitation force inside? So gravitation field is also inside. Okay, so gravitation field is always parallel to gravitation force, or in the same direction as gravitation force. Okay, what is its unit? Unit is force by mass, that means Newton per kg. That's the unit of gravitation field. Okay, so whatever questions you are solving for gravitation force, same we can do for gravitation field also. Only thing is we have to divide with this mass. So gravitation field is of this mass, so it depends on this mass only. It depends on this mass and distance from this mass. That is the gravitation field strength. Okay, what this gm by x square is? What is the strength of gravitation field at a particular point? As you go away from the mass, gravitation field strength is going to decrease, and at infinity it becomes zero. Okay, strength of gravitation field. Right? The strength of gravitation field formula is what? Gm by x square. Gm by x square. Now on this one there are questions. What question can we ask? Represent this gravitation field in the form of density. Okay. Represent gravitation field in terms of density. In terms of density. In terms of density for, let's say, what we are taking as particle, let's say sphere. For a sphere of radius r. Okay, so what we are going to do, we are taking one small sphere here. Okay, this is its radius, and where we are writing its gravitation field, maybe somewhere outside at distance x. Okay, so what we will do, we know that at this point P, the gravitation field is actually g mass of the sphere by x square. Now what is mass? He is saying that write in terms of density. The mass is actually density into volume. Mass is density into volume. Okay, density I am considering as rho. So what you will write? Rho into 4 by 3 pi r cube. That's it. Yes, that we are going to put in this one. So g into rho into 4 pi r cube by 3x square. Okay, so same thing we are writing this way. Right? So this is gravitation field written in terms of density for a spherical object. Or you can say planet also. Planet also will be writing same way. Correct or not? Yes. Okay. So this is your gravitation field. Then acceleration. Acceleration due to gravitation force. I am not saying acceleration due to gravity. Okay, I am saying acceleration due to gravitation. Gravitation force. Now what that is? Acceleration means what? You know that it is F by m. Right? And if we are talking about two particles, let's say m and this is n. Separation between them is x. So this acceleration is what? Gmm by x square by m. Whose acceleration is this? This mass acceleration, which will be in this direction. Okay, so m and m gets cancelled, it is gm by x square. Now, if you look at this, this is actually the value of gravitation field strength here. Same thing, no, F by m only. Okay, so gm by x square. So, in this one, acceleration of this mass depends on what? This mass and distance from this mass. Same way, if suppose it's acceleration I am finding, then what will come? Acceleration of capital M. Acceleration of capital M will be g m m by x square by which mass? Capital M. So its acceleration will be that. What's going to come? Gm by x square. Okay, so if suppose I am talking about our acceleration. Our acceleration depends on how much is the mass of Earth, and acceleration of Earth depends on how much is our mass. So in that case only, if you are talking about us, okay, our acceleration is huge. You know the 9.8 meter per second square, our acceleration, because of the mass of Earth. But Earth acceleration because of our mass, negligible. It hardly moves. Because our mass here is what we say, 2 kg, 3 kg, 50 kg, 1000 kg. But this is actually already 10 to the power minus 11. Okay, already this is 10 to the power minus 11. And next, radius of the earth we will take at least 6400 kilometers. So this acceleration becomes negligible. But when you come over here, this is the mass of earth 6 into 10 to the power 24 kg. So this becomes 9.8 in case of earth. Okay. So acceleration due to gravitation forces this. Okay, fine. Alright. Now let's talk about acceleration due to gravity. Acceleration due to gravity. Now this is also acceleration formula will be same only, yes, formula is same. But when you talk about acceleration due to gravity, we represent this with g. Okay, and its value is gm by r square. What is m? Mass of earth, r, radius of earth. This is where on the surface of earth. On the surface of earth, value of acceleration due to gravity is gm by r square. Okay, but there are certain variations in this. What variations are there? Variations are there that if you go to certain height, then G value changes. If you go slightly below the surface of the earth, it changes. Okay, and there is a variation even on the equator, its value is something else, and on the pole itself it's something else. Okay, so that's we are going to see now. Variation in the value of G. Variation in the value of G. Okay, so what it is? Say at certain height, at some height. Okay, so at some height when we are saying, let's take earth here. Okay, radius is r, and we are talking certain height, let's say here. Here is the particle, so this is h. So what will happen? This is r, and this is h. So this point is p. So what is acceleration due to gravity at point P? We'll say acceleration due to gravity at point P is g mass of earth by r plus h whole square. Because formula is this. So gm by r plus h whole square. This is at P. Actual value is this only. But two things in this we have. If h is very small as compared to r, then we get one formula. Now see. What we are going to do, this g at P, we are going to write as gm. Okay. From here, I am going to take r common. I am going to take r outside. So when you take r outside, it will become r square, and here is 1 plus h by r whole square. Okay, this is 1 plus h. If you want to see that, you just multiply r square, r inside. This is r square, Okay, when it go inside, it will become r over here. Here is also r. So same thing will come again. R plus h whole square. Okay, I hope this is not a problem to you how it came. If there is a problem, then what we should do? Gm multiply by r square and divide with r square. No problem in that, right? So divide also with r square. So here is r plus h whole square. Now what? This you take inside. So gm by r square, this is as it is. And you took this one inside. So r plus h whole square by r square. Okay. Correct. Square only. So what is now? 1 plus h by r. That's what I have. Clear? Now in this one, what is this? This is g. This one. So gp becomes g by 1 plus h by r whole square. Now take this one up. 1 plus h by r to the power minus 2. Okay, and now we are saying h is very small as compared to r. H means maybe around 2 kilometers, 5 kilometers, 10 kilometers. Radius is how much? 6,400 kilometers. So it's negligible. 10 kilometers is what? 10 by 6,400, very less. Okay, so if it's very small, then we can write this as g into 1 minus 2h by r. Okay, how? By binomial expansion. What is binomial expansion? It's 1 plus x to the power n. Okay, and x is very small as compared to 1. Here also when we are saying h is very small as compared to r, means this term is very small as compared to 1. So in that case, we can write this is equal to 1 plus nx. This is binomial expansion. Same thing we did here, 1 minus 2h by r. So at height h, acceleration due to gravity, we write as 1 minus 2h by r. Okay, this is at certain height, but if suppose that h is comparable to r, maybe h is something like 1000 kilometers, 500 kilometers, then we will not use this formula. Then what we will use? This exact formula. From here we will calculate. Okay. So on this one, what question will be asked from us? They will ask us that how much is the percentage change in gravitation, acceleration due to gravity is coming if you are going about 10 kilometers, 5 kilometers, like that questions are coming. Okay, percentage change in value of g. Okay, so percentage change, how to find? Percentage change is g on the surface minus g at certain height, let's say this is p only, by g into 100. Okay, so what it is? G is as it is, and this gp is what? G into 1 minus 2h by r by g into 100. So g is getting cancelled, right? Okay, g take common. Then 1 minus 1 plus 2h by r by g into 100. What we are getting? G is g cancelled. So it is actually 2h by r into 100. Percentage. So that's just this we can apply. Yes, you can apply just 2h by r into 100 will give us percentage. Is the percentage decrease, percentage increase, or percentage change? This is the value. Okay. Alright. Then if you are going below the surface of the earth, what is the change? Okay. So in this case, this is the earth. Okay, radius is r. And suppose that you are digging from here and you reached here. Okay, to depth d. Now we want to know what is the acceleration due to gravity value here. Let's say this point is again p. Okay, g at p we want to know. But on the surface we know gm by r square. So how to solve this one? Okay, So this one will be solved with the help of Gauss law. Gauss law we can apply in this one. Yes, we can apply in this one. What was Gauss law if you remember in electrostatics? We said that net flux through enclosed surface or Gaussian surface is equal to charge inside by epsilon naught. And this flux was what actually? This flux was E dot ds. Okay, same thing we'll do here. Q will be replaced by the mass inside, and this epsilon naught will change into in terms of gravitation constant. Okay, so in gravitation, the same Gauss law changes into E dot ds equal to minus 4 pi g mass inside. 4 pi g mass inside. How? Only epsilon naught we have to change, no? And what is the relation? See, gravitation force is actually gm square by r square, whereas electrostatic force is 1 by 4 pi epsilon naught q square by r square. Right or not? Now we have to get the value of epsilon naught. So epsilon naught's place, or you say that, don't see this, you get confused with this. Gravitation constant, we are comparing it with 1 by 4 pi epsilon naught. So 1 by epsilon naught is equal to what? 4 pi g. So in place of 1 by epsilon naught, what we have written? 4 pi g. Why minus? Because this is attraction force. This one depends on how much, what kind of charge is there. Okay, so normally we take positive charge only when electrostatic we talk. Maximum cases we will take positive charge in the right. And electrostatic field we show outwards. But this is mass and it is always inward. So that's why here we are writing minus 4 pi g into mass. Okay, so this is Gauss law. Gauss law in gravitation. Okay, this is important. Note this one. But here I am not interested in this minus. I am interested only in the value of acceleration due to gravity. Acceleration due to gravity and gravitation field values are same, right? So that's what we will do. So first thing is make Gauss law here. Gaussian surface. This is Gaussian surface. What is its radius? The radius is r minus d. Okay, let's put it here. So in place of this E, I am writing G only, okay? So G at P into surface area. What is that? 4 pi r minus d whole square equal to 4 pi g mass inside. How much is mass inside this? Okay, so mass inside how to find? So density into volume. Okay, density into the small volume. Okay, so density let's assume is rho and volume is 4 by 3 pi r minus d whole cube. So this 4 pi and this 4 pi cancel. R minus d whole square and r minus d whole cube here. So what I am getting? G at P is equal to 4 pi g rho by 3 into r minus d. Now this rho I am writing. Rho is what? Rho is mass by volume. M by 4 by 3 pi r cube. Okay, so put it 4 by 3 pi g into m by 4 by 3 pi r cube, and here is r minus d. Okay, so this 4 by 3 pi gets cancelled. Okay, what we are getting? Gm by r square into r minus d by r. This r cube I have written as r square and r. What we are getting? This is what? G. So G into 1 minus d by r. Now I could have told you this direct, but in that case I would not have told you the Gaussian law in gravitation. Okay, so Gauss law in gravitation is also important. It helps you in a lot of places. So that's why you note this. Okay. So what is the gravitation acceleration due to gravity value? Inside, it is G into 1 minus d by r. G into 1 minus d by r. Now, in this one also, many questions are there. They will ask you direct answer, or sometimes they'll ask you at height h, whatever is the value of gravitation, acceleration due to gravity. Same value we have found inside. So, what is the relation between d and h? We'll do that question. See, question is at height h, above the surface of earth, above the surface of earth, and at depth d, below the surface of earth, g value is same. G value is same. Then relation. Then find relation between h and d. Relation between h and d. Easy. Okay. At height h, what is the value of g? 1 minus 2h by r. Below, what is the value? 1 minus d by r. So answer d equal to 2h. Like this, many questions are there. Okay, so below the surface of the earth also we got what is the acceleration due to gravity. At height h, what is the acceleration due to gravity? That also we have found. Then, what is there? Acceleration due to gravity because of rotation of the earth. Earth is rotating, we all know. Okay, so this is the axis and this is the omega with which it's rotating. Okay, and suppose I want to find at any point like this. Okay, this point is P and this angle is theta. Okay, so I know that this particle point P is moving in the circle like this because earth is rotating in this way. So this particle will be moving like this. This particle here will be moving like this. This particle will be moving like this. So whose radius is biggest? Equator. This is equator. Okay. Now what's happening on this particle? If its mass is m, then earth is applying the force. Earth is applying the force from where? From the center. From the center, because center of mass is this. Okay. So earth is applying the force in this way. This is it. Correct? And because it's moving in circle, so on this one there will be centrifugal force like this. Okay, a component of centrifugal force will be in this way. This is theta. So what is that component? M omega square r cos theta. So net force with which earth is attracting it in this direction, what that is going to be? So net force F minus m omega square r cos theta. Now what is this F? F is mg. F is mg. Then what this force we call? We say that this force is mg dash. Because g only is changing, no, mass never changes. M and m gets cancelled. So g dash value is g minus omega square r cos theta. Now r is what? R is this radius. And capital R is radius of earth. Okay, this is small r and this is capital R here. Then relation is there between small r and capital R. What is that relation? This is 90 minus theta. So we'll say sine 90 minus theta equal to r by capital R. Small r is actually r cos theta. Put it here, G minus omega square r cos theta into cos theta. So formula we get is G minus omega square r cos square theta. This is acceleration due to gravity because of rotation of Earth. At the equator, what happens? Theta becomes 0 at this point. Then what is the value of G here? Effective value is G minus omega square r. At poles, theta is 90. So at G dash value is G on, exact value. Because theta is 90 means this is 0. So G dash is G. Whereas here it is G minus omega square r. G minus omega square r. So here value of G is least. Okay, so this is the value of G because of rotation of the earth. Okay, just a moment. Yes, students. So this is acceleration due to gravity. Okay. Then what more we have? We talk about gravitation potential energy. Gravitation potential energy. Now potential energy we all know, negative of work done by conservative force is equal to change in potential energy. Okay. So it's a work done by gravitation force. So F dx. Okay. Work done by gravitation force is what? G m1 m2 by x square into dx from position 1 to position 2. Okay. So G m1 m2 is constant. Dx by x square I told you minus 1 by x. This is x1 to x2. So work done by gravitation force is this. What will be writing? 1 by x2 minus 1 by x1 or 1 by x1 minus 1 by x2. Why? Because negative sign is there. This is work done. Okay. Now this is equal to negative of change in potential energy. So what is the final formula when we talk about gravitation potential energy? It is actually G m1 m2 by separation between the two charges, and it's negative, minus G m1 m2 by r. Why negative? Because attraction force is there. So attraction force potential energy is always negative. And electrostatics also, if you are taking one charge positive, other charge negative, potential energy will be negative. Here also it comes negative because attraction force is there. So minus G m1 m2 by r. That means if there are two particles, r at separation of r, then potential energy is this. Okay, clear? So remember the formula. Then what is the relation between, in general here we have written already. So what is general relation between potential energy and force? This is the relation. D equal to minus FTR. Why minus? I said no, negative of change in potential energy. Okay. Or F is equal to minus du by dr. So if there is a function given for potential energy and they ask you to find force, F equal to minus du by dr. Differentiate the potential energy function, you will be getting conservative force value. Okay. Many times there will be one type of question you will be seeing. Okay, it will be, I don't remember exactly, but I'm just writing the format. A by r to the power 6 minus b by r to the power 4, something like that. And they ask you what is the, where the body will be in equilibrium. So what you will do, just differentiate that with respect to r, then force you will be getting. And equilibrium means force will be 0. So if you differentiate that, and then equate it with 0, you will be getting some value of R. That's what the question is asking. Okay. So find the position at which it's in equilibrium. The body is in equilibrium. This function is given. To differentiate, equate it with 0. Because differentiation of potential energy function gives you force. And equilibrium means is net force 0. Okay. So F equal to minus du by dr. Very important. Then what next? Next is potential. Gravitation potential. Gravitation potential. What is gravitation potential? Gravitation potential energy per unit mass. Gravitation potential energy per unit mass. Now suppose we have a mass m and its gravitation potential I have to find at distance r. So what I will do? I will just write gravitation potential energy by bringing any other mass over here. Say here is m. I brought it, imaginary. So I will write gravitation potential energy as minus g mm by r. By then mass, which mass? M only, which you brought. So what we are getting? Minus gm by r. Okay, what is its unit? Joule per kg. This is gravitation potential. It's also negative. Yes, it's always negative because it's force is attraction force. So potential is always negative. So potential energy negative and potential is also negative. Potential and gravitation field intensity, does they have any relation? Yes. What is it? E, which is gravitation field intensity, equal to minus dV by dr. What is this V? This is potential. E equal to minus dV by dr or dV equal to minus E dr. Same relations we use in electrostatics. Same are here. No change. E equal to minus dV by dr, dV equal to minus E dr. Remember that. In this one, on this one, less questions are asked, very less. Very less. On this one, there will be questions. Yeah. But on this one as such, very less questions are there. These questions will be more in electrostatics. Okay. So dV equal to minus E dr and E equal to minus dV by dr and the formula for the potential minus Gm by R. Okay. Now let's do one question on equilibrium. Equilibrium we didn't do any question. Again, this is more into electrostatics, but one question we will do here also. So here is mass m and suppose here mass is 9m. Both are same type of masses. This is m, this is 9m and separation between them is 2m. Okay, so find the position along the line joining two masses where gravitation field is 0. Gravitation field is 0. Or the same question I could have asked is, where shall I keep the third mass so that the net force on that is 0? Both are same questions. Okay. So how to do it? Will it be along the line joining two charges? Yes, because two masses. He's asking that only. So suppose somewhere here gravitation field will be 0. Where that point should be? Closer to smaller mass. So maybe this is x. Okay. And what I'm going to keep here, let's say 1 kg. 1 kg is the mass. So what this m is doing? It is attracting like this. What this 9m is doing? It is attracting like this. Then only the net force will be 0. Okay. So let's equate. Force because of this equal to force because of this. So G into m by x square. So when you are keeping 1 kg, the force that you are writing, in fact that is gravitation field strength only, Gm by x square. Here G 9m by 2 minus x whole square. So G and m gets cancelled. What we have is 9x square equal to 2 minus x whole square. Take square root of this. This is 3x equal to 2 minus x. Bring this one here, that is 4x equal to 2. So x comes out to be 1 by 2. So at 1 by 2 meter, you will have zero gravitation field or no force on any mass. Okay. This kind of questions are common. So this can be asked from you. Then what now? What more? Now we are going to talk about energy. Okay, energy of satellite which is orbiting around the earth, or you can talk about planet which is orbiting around the sun. Okay. What is the energy? So suppose this is earth. Radius is r. There is earth here. Okay, and the satellites are there. This is the orbit of the satellite. Okay. Mass is m. Satellite. So what energy this possesses? We know that it's moving with velocity. Right. And it is also orbiting around the earth. So earth is attracting it. It is in the gravitation field of the earth. Yes. Okay. So this planet, or this satellite rather, its total energy is sum of potential energy and kinetic energy. Okay, and if suppose that this radius of the orbit is small r, then potential energy is minus gmm by r, gm1 m2 by r. Why? Because the mass of earth is at its center. Gmm by r plus half mv square. Now the question is, what is this v? We call it as orbital velocity. This is orbital velocity. Now what is orbital velocity? The question is, on this one, definitely there is force required by earth. Okay, so attraction force is there. Okay, and there is centrifugal force also acting outside. Okay, so centrifugal force is actually balanced by the attraction force of earth. So we can write this as G m m by r square is equal to m v square by r. M and m gets cancelled, r and r gets cancelled. So what is v? V is root gm by r. This is orbital velocity. If you want to convert this in small g terms, we can do that. Multiply with r, divide with r. Then what will happen? Sorry, made a mistake. 1 minute. Multiply with r square, and here also r square. Okay, so what will happen? This gm by r square, that's only small g. This. Okay, then what is left? R square by r. So then it becomes g by r into r square, which you can write outside or you can write inside, that's your wish. Okay, if radius of the orbit is almost equal to the radius of the earth, that means it is very close to the surface, then we can write this as capital R. Then it comes out to be root gr. In that case only, otherwise not. If radius of the orbit is equal to radius of the earth, that means it's very close to the surface of the earth, then it will be root gr. Okay, be careful. Okay, so what you will do here, I am going to write this is minus gmm by r plus half m. What is orbital velocity? Root gm by r. So here I will be writing gm by r. So what is total energy? Minus gmm by 2r. So what I am trying to say you with this, first of all, I am trying to tell you how to calculate. Okay, orbital velocities formula I give you. What is potential energy and what is kinetic energy and what is total energy relation. Okay, so potential energy is double of total energy because this is minus gmm by 2r and this is minus gmm by r. Second thing, kinetic energy and total energy, their value is same. Both have written total energy only. Kinetic energy is equal to total energy and potential energy is double of total energy as well as kinetic energy. So these two are very important relation. Remember that. Okay. So orbital velocity we saw, total energy of the system we saw right now. Then what more is there? Escape velocity. Escape means what? You want to escape out of the gravitation field of Earth. So first question is, to what distance gravitation of field of Earth is there? To infinite distance. So where you want to go? To infinity. Okay. When you say escape velocity, that means you want to go to infinite distance. This is Earth. Okay. We are projecting a particle from here and we are sending it to what? Infinity. So escape velocity here we are writing as Ve. This is mass of Earth. This is radius of Earth. Okay. Just a moment. Yeah. So escape velocity, we are projecting it and it is going where? Infinity. Infinity, what will be potential energy? 0. Why 0? Minus g mm by infinite distance. 0. Okay. Now you are projecting it with escape velocity. Escape velocity is what? Minimum velocity of projection. Minimum velocity of projection required to escape from gravitation field of Earth. Gravitation field of Earth. So when you say minimum, then what you expect? What will be velocity at infinity? That means this is the topmost point. No, that is where you wanted to go. You reach the topmost point, then what will be your velocity? 0. So your velocity is also 0. Then what you can do? Conserve energy here and here. Conservation of energy will do. Okay. So at projection point, what is the energy? Both potential and kinetic you have. At the final point, both have become 0. Okay. So total energy at projection should be equal to total energy at infinity. Okay, what is total energy at projection? Half mve square is the kinetic energy minus g mm by r is potential energy, whereas here both are 0. So from here we will be getting escape velocity value, and what is that? 2 gm by r. Is it fixed? Yes, everything is fixed. G is fixed, m is fixed, r is fixed. It comes out to be 11.2 kilometers per second. This is escape velocity, but if suppose you are projecting it with more than this velocity, then velocity here will not be 0. Here velocity will be something else. Some velocity will be there, and that velocity is called interstellar velocity. Okay, so I am just giving you the information. If velocity of projection, if velocity of projection is more than escape velocity, then particle moves with interstellar velocity. interstellar velocity in vacuum. Interstellar velocity at infinity. Okay, so it will be moving with interstellar velocity. Right. And what is the relation between escape velocity and orbital velocity? Orbital velocity is root gm by r. But if suppose that the particle or the planet is close to the surface of Earth, planet is close to the surface of Earth. Normally, which satellite will be close? Planet, I am writing. Satellite. If satellite is close to the surface of Earth, so which satellite used to be close? Polar satellites. Polar satellite used to be closer to the surface. Okay. In that case, what is the orbital velocity? You can write as root gm by r. Okay, in this case alone, and escape velocity is root 2 gm by r. Okay, so there is a relation between them. What is that? Ve is equal to root 2 times orbital velocity. Remember that this relation is not always true. So be careful. Okay, be careful. If the radius is equal to the radius of the Earth, then only you can use it. Otherwise, we should not be using. Okay, so this is it. Gravitation. Okay, many things are there in this one which are exactly similar to electrostatics. And when we talk about the total energy and the satellite is orbiting around the Earth, it is very similar to atomic physics. Okay, so three things are there which is the combination over here. And as I said that this is important chapter. Minimum 8 marks questions will be there in which gravitation will be there. Okay, so do well. Theory part we have covered, certain numericals also I told you. Just go through that. Very easy chapter it is. Finish it. Okay, that's it for today. See you tomorrow, students. Bye bye.
Thank you.